What is going on, subscribers and others? Welcome to part 12 of our machine learning tutorial series. In this tutorial, what we're going to be talking about is testing our assumptions. So up until this point, it's been, I would say, rather hand-wavy in the sense that I have just said, hey, these are the algorithms, and whatever they output, these are the answers to those algorithms, and we have done linear regression and R-squared and all this. And so the question is, we need to actually kind of test all of these assumptions. So we've got actually two major algorithms. One is the equation for the best fit line, and the other one is the R-squared, or coefficient of determination. So we've got these two major algorithms that are also comprised of many other algorithms. And as we even saw just a few videos ago, the misplacement of a single parentheses changes everything and completely ruins the entire thing. So we need to be able to test to make sure things are working as intended. So in the world of programming, there's a similar kind of field and structure called unit testing, where we test each little small unit basically that we can in a program, and this kind of helps us from getting into trouble. Now, this is not going to be unit testing, but the idea is fairly similar. We've got a lot of ideas, we've got a lot of inner working parts, and we want to at least test them to make sure. The easiest way we can do that is by working with sample data, and by sample data that we have the power to change, so that we can create a data set that is a more linear data set, and or at least the relationship is more linear, and then we can test to make sure, is R-squared better, higher, right? And then also just test our best fit line. But for the most part, we're actually going to be testing R-squared. And if the data is not more linear, we can make it more spread apart. R-squared should be lower, and so on. So anyways, let's go ahead and do that, and we can also confirm visually that the best fit line is indeed working just by looking at it and seeing whether or not it is indeed a best fit line, or what looks to be a best fit line. So first, what we're going to go ahead and do is we're going to import random, because we're going to be using random numbers. Everybody, the obligatory pseudo-random. If you don't say it's pseudo-random, someone absolutely feels the desire and urge to comment and say, but it is not real random. So anyways, pseudo-random. There you go, you nitpickers. Okay, so what we're going to do is just right under here, we're going to say define create underscore data set. And then here we're going to have, we're just going to pass some parameters. First is how much, like how many data points do we actually want to create here. And then we're going to say, we'll pass variance, and this will be how variable do we want this data set to be. Then we're going to pass step, and step will just be how far on average to step up the y value per point, and we'll assign a default value there. And then finally, we're going to do correlation, and this is where we can just pass a value and say we want correlation to be positive, negative, or none. What we're going to do here is correlation, hold on. So correlation will either be true or false. And then if it is true, to get it to go to be a positive correlation, step will just be some positive number, right? Because that's changing y. And to be a negative correlation, you would just change this to a negative number, right? So, and in fact, another way we could do it is we could actually say correlation is positive or negative, and if it's negative, you do a multiplication of the step. And that's actually probably a better way to do it. Either way would work, but we'll do it that way, actually. So the first thing that we're going to do is, well, we would want to be able to, at the end of this, I always like to build a skeleton function first. So at the end of it, what is the objective? And that would be to return the NumPy array of the x's. And for now, again, we will specify the data type so we don't forget this later on, because it's probably going to be useful later on. So we'll say float 64. So that returns the x's, and then we also need to return y values, so y's, and then d type equals np float 64. Okay, So that's the objective that we want to do, and then now what we want to do is start creating at least some random values. So the first thing we're going to say is we're going to start with val equals 1. So that's just going to be the first value for y basically, and then we're just going to say y is an empty list, and then we could say something like for I in range of, and what should this range be? Well, it should be HM for how many, right? So for range in HM, what are we going to do? Well, we're going to say y equals the val plus random.randRange, and it should be random.randRange from the negative variance to the positive variance. So some range in there is what we want to do first. And then we're going to say y's.append that y. So here we would just be iterating through the range using that how much variable, and then we're just appending that current value plus a random one. So this would give us data, but really no correlation if we actually wanted that data. So then what we would ask is, so keep in mind that y is literally the val, so it's just that starting value and then a variance from that starting value. So this would be pretty worthless at the moment. It would just be somewhat varied, but not by much. Well, it depends on what you said the variance was. Anyway, so then what you could say now is if correlation and correlation equals positive, what we could do is val plus equals step, which would in this case default to 2. And then elif correlation and correlation equals negative, what do we want to do? Well, val minus equals step. Finally, at the end of the day, all we're going to do is now we've got the y's, so we just need some x's. So we could say something like x's equals, and we'll just do a one-line for loop. For I in range of what? The len of y's. That's good enough. Or you could do how much for that matter. Anyway, so now we've got what we need, and we're returning some x's and y's. So to create a sample data set, we could do something like, and for example, we could leave this here for now, but I'm going to comment it out just so we know that we're working with our new data instead. So underneath this, you could create a new data set, but I guess we'll create it down here underneath all these other functions. So you could say something like x's, y's equals create data set, and then let's say we did a recall that it's how much variance, the step, and the correlation. So let's say we said we want 40 data points with a variance of 40, the step will be 2, and correlation will make that positive. So now we have x's, y's, we can print r squared and all that fun stuff, and let's go ahead and run that real quick. And in fact, are we still, yeah, we're still graphing that prediction, so we'll get rid of the prediction. We could actually leave the prediction, that might be kind of interesting. For now, that we might run into trouble. I'm not really sure if we're going to get in trouble for that or not, but we'll just do that, and let's run it and see. We might have to change something else, but I think that would be everything we would change. Awesome. So here's our data set, and sure enough, there's a nice best fit line for us, and we see that we would kind of agree with that visually. Let's go and graph that other plot though, that one, and this will be a G prediction. I don't even see it. It was for x equals 8. I guess it would be right on the line, and then we're plotting the regression line, so I'm guessing the line is just going right over it, probably. It's just being drawn over it. Still not seeing it, however. It was x equals 8, right? So it should be that. It's probably this little plot right here. I'll zoom in. It's there. I don't know if you'll be able to see that on the video, but there is indeed a plot there, and in fact we could do something like, I think with scatter it'll be s equals, and then let's try 100. So this is like for the size, and indeed there is a huge green there. So okay, anyway, so there's our prediction. As you should expect, it's perfectly on the line. So we're going to close this out, And so now, how would we test our assumption? Well, recall that we've got how much and then variance. So if I took variance, which is currently 40, and we saw that it was like 0.5, I think, for r squared. Let's look at it again. Well, since it's random data, this time it was 0.6. Okay. So in theory, if we decrease the variance, what should happen? Well, what should happen is that number should go down pretty significantly so long as we decrease variance significantly. So let's do it. Let's do 10. We can save and run that. And as you can see, it's much tighter. Everything's there. And sure enough, the coefficient of determination is very, very strong. It's 0.92, much better than before. And what if we changed this to an 80 now? It should be less than 0.6. And sure enough, it is less than 0.6. And so what you can begin to do is automatically write a program that just simply calculates the coefficient of determination for just a sample data set. And you would just make sure, for example, that you'd start with 40, save that number, and then you would change that to 10, and hopefully the coefficient of determination was less than this initial number, and then if you went greater, it should be greater, and so on. That would be a way to test just that. We'll call it a unit. In theory, you could build a unit test out of this, but this isn't quite yet a unit test. But anyway, so you can test that. And then sure enough, the other thing you could do is, while initially we had a positive correlation, if we change this to false, we should get quite an ugly data set. Sure enough, we do. And the coefficient of determination is almost 0, which is absolutely not surprising because that almost looks like a completely flat line. And sure enough, this data is completely nonlinear. So if you did have a data set and you were trying to run linear regression on this data set, and you came back with an r squared that was this number that's like 0.0007, you would probably be smart enough to decide, hey, my data is actually not linear. We can't quite do linear regression with this data. That said, you can do other forms of classification with the data, or not just classification, but you can do other forms of machine learning. I'm thinking classification with your data. It doesn't necessarily have to be linear. And in fact, a lot of classification should be linear in some way, but we'll get there. Anyway, that's enough for now, I think, but just kind of keep in mind that when you create big scripts like we have here and big programs that are kind of based on a lot of things, you want to make sure that it's about right. We could check the best fit line ourselves kind of visually, but r squared, we could not really totally test that, but you could definitely program something that would go through and, like I was saying, check to make sure r squared was acting according to our assumption and our knowledge of how it ought to act. So we're basically done with regression, but I want to make a quick edit to this video to cover two pretty important things. One is a fundamental aspect to machine learning that might be getting overlooked using the really simple example that we've used here. And then two, I made an error that I think is bad enough that we want to cover it. Plus, I think you can learn a little bit from the mistake that I made. So let's pop over to the code and address these two things, hopefully pretty quickly. So first of all, looking at the data, I'm going to change this from 1% basically to 10% now. We're going to run that, and we're going to see that it's basically an exact copy of like the data leading up, just shifted in price a bit, right? So coming over here, it's basically the same. This version is squished up a little bit, and that's just because the blue line is the prediction line that plots even on the weekends and holidays, whereas over here the stock price only occurs during Monday to Friday and not on holidays as well. So anyways, basically an exact match, just higher in price. And the reason is kind of twofold. One, we've created a linear model that is going to attempt to do this, but then also we've made a mistake. So we'll address kind of both. But anyway, the first thing is, and the biggest mistake, actually there was two mistakes. One I noticed in the video just going back over it, I'm pretty sure it was here. There was also a colon at the end of the X. I'm not sure why that was there. No one actually brought out that one. I just happened to see it right before filming this one. Anyway, that basically is x equals x, right? All that says is x up to forecast out and then finish the whole thing, right? So that doesn't do anything. So that was just a typo. But then you get to this point, and we're still kind of in a world of hurt because x, what we were intending to do was say, okay, x is the first, let's say in this case it's 10%. Yeah, so we're saying X is the first 90% of data. This is the stuff we're going to train against, and then we're saying X lately, and our objective here was to say X lately is the last 10%. But instead what we've done is we've sliced X and redefined X here, and then sliced X after it's already been redefined. So this is actually minus forecast out of the 90%. So obviously simplifying things a little bit, this is the basically up to 90%, and this is the last 10% of that 90%. It's a little more, but anyway. So that's a failure in logic. Okay, so really to fix that, you just cut that, paste it there, and there you have it. Now this is still going to create a model that's relatively akin and very similar to what we've already seen. And again, this is because we're using linear regression. It's going to create a linear model that resembles what we've already seen. So again, you've got some jagged, then you got to jump up, and then price. It's a little different, but it's very, very similar. Okay, so anyway, that's just given what we've done and how we've trained it, that's going to happen. So now let's talk about the last thing, which is the fundamentals of, what kind of features should you train against. So what was the objective here? First of all, let me just say the reason why we did it this way is just for simplicity's sake. We're just trying to do a really simple regression example. But let's say, regardless of whether or not you're interested in stock investing, this problem is, every machine learning problem is going to likely be a somewhat complex problem. So you have to think pretty logically about the features that you choose to use. So looking at this, which of these things hinges directly on price or will directly impact price? Right? Well, obviously adjusted close will. What about high minus low percent? Does it matter what the price is? No, it's a percent, right? It's a normalized value, so that doesn't have anything to do with price. How about percent change? No, right? These maybe volatility, right? Maybe magnitude, same thing with high minus low percent, volatility and like direction maybe, but not price. What about volume? No, not price, right? This is just magnitude kind of fluctuation maybe, stuff like that, volatility. So the only thing that really hinges on price is adjusted close. To illustrate that, despite training on a future value that is indeed price, what we can do is we can actually drop adjusted close from the features. And what do you think? When we drop this, what do you think is going to happen before we graph it? Is that going to create a similar line that follows price? Is it going to be a falling price, upward price, flat line? What's it going to create for the prediction? So think about that. We run it really quick, and we'll get our answer. And the answer is not going to be probably what we were hoping for, right? It's just more of a flat line. And why do we get this, right? Well, the high minus low percent, you probably had very similar high minus low percents back when price was $400, $600, $800, right? Not big differences. The only thing that might be sort of impactful is the adjusted volume, since probably less people are quickly flipping an $800 stock as opposed to a $50 stock or something like that. But regardless, these just aren't the greatest features. So thinking about your problem, in this case it was stock investing, what is a stock price indicative of? It's indicative of the entire company's value. Let's think of Google, for example, like $500 billion, I think. Why is Google worth $500 billion? Is it because of the adjusted close, high minus low percent change in adjusted volume? I mean, no. Come on, be logical about it. You know that's not the case. There are people who believe in pattern recognition and stuff like this, but or at least chart patterns in stocks. And sorry, but it's been tested. There's plenty of research done that it doesn't work. But anyway, some people still believe it. But fundamentally, why is Google worth $500 billion? It's not because of this stuff. Fundamentally, Google's worth $500 billion because of things like its quarterly earnings, its price to earnings to growth, its book value, and so on. These are the things that value the company. So if you wanted to predict stock price, you would use features that attempt to predict the company's overall value. And then from there, you can divide that by outstanding shares and get a specific share price for the company. But anyway, this was just meant to be a very simple example. If you want to see a more complex example of doing investing with features and fundamental features of companies, I do have a tutorial series out for that. It's like 30 something videos if I recall, or maybe 20 or something, but it's kind of tedious because you've got quarterly earnings, which is every quarter, and then you've got things like price to earnings to growth, which you could measure all the time, book value, price to book, you can measure all the time, and so on. So a lot of these things, and also just the entire company's value, is a changes as throughout the day. So anyway, it can get really complex really quick. So we just wanted to use a really simple example, but if you are looking for a more complex version, I do have one. But anyways, that's it with regression. Hopefully you can learn from my mistakes down here. I'll probably continue making mistakes, and you'll probably make mistakes too. And that's just like part of it, honestly. So luckily we could visualize this and we could catch it, but a lot of times you're not going to be able to visually catch it. So you want to like read and reread and all that your code, but still you're going to make mistakes. So unless you're a robot or something. So anyways, hopefully you can learn from my mistakes. Otherwise, we're going to be leaving regression behind now and traversing into classification. So stay tuned for that. As always, thanks for watching.